we are talking about electromagnetic wave. Uh, just a quick reminder that the coefficient of Z is shown as K, okay, which is of course a specific constant, and it's called wave number. Uh, Now, uh, if it is if it is not a plane wave, okay, then there will be something else. The notations are also different. The notation can be beta or gamma, okay. Uh, i- but these parts we're not including in this course because we are considering a wireless link where you launch the signal and shortly after the antenna area, I mean, after the initial propagation zone, it takes on the form of plane wave. So we can safely use K throughout the rest of the link. And the receiver is never put that close to the transmitting antenna, and it is not allowed for any, I mean, wireless link. It is not expected or uh, I mean, it's sort of prohibited that you put the receiving antenna within that very close region of the transmitting antenna. And you don't need to, right? Because, I mean, if you are located that close, you could connect using some wire or something. Okay. So, and that region is very small. Anyway, so considering plane wave, we're using K. Uh, but we know that the wave can also be a guided wave when you use the wave in a circuit. In that case, it can be either plane wave or not. The guided wave the, has the form that depends on the type of the guide that you use. So it can be either plane wave or something else. If it is plane wave in the circuit, within the guided in the form of guided wave. If you still have plane wave, then you can again use K. Okay. But a lot of times it is not a plane wave when it is guided wave, and then you have to use something else. It will be either beta or gamma. Beta, if the propagation path you can consider lossless, then it is beta. Give me a second. And if it is not lossless, then it is gamma. Okay, but beta and gamma we are not including in this course. Okay, so for the case of wave, we have variation in both domains, time and space, and there's the difference from your considerations in the previous years in first year electrical course, where you considered sinusoidal variation only in the time domain. But now there are simultaneous variations in both time and space, and it is called cycle when you complete one whole variation, okay, either in time or space. And we know what phase position is. Yesterday I also actually mentioned that any position within the cycle you indicate using a phase between 0 and twice pi. Now, when you restrict to time domain, then the time that it takes to complete one cycle is called period. Okay. And the number of periods that is completed in 1 second is called frequency, you all know. Now, when you complete one cycle in the space, okay, you cover a distance. So consider a particular time instant, and you find that a cycle is completed over the space. over a particular distance. That distance is called wavelength. Okay. Yeah, I think you all understand that too. But the point I wanna clarify here is that let's assume that you can you're looking at the wave at different time instants. Okay, and every time you find the cycles completed over this space, and you can see, okay, all these things are visible, let's assume, and you have a marker and you can mark the different cycles, okay, like I have done here, ABCD. Well, now if you look at the wave after a whole time period, okay, that is t prime plus complete t. Here t represents one period. Okay, that's the time it takes to complete one cycle in time. So if you look at it one whole period, then you'll find that uh, the cycle marked as B is now replaced by the cycle marked as A. Okay, completely. I mean, you have a new alignment. One cycle has taken this position of its subsequent cycle. That's how you have complete shifting of positions in the space. When you are considering a time gap of complete one period. Similarly, if you take complete two period, okay, when this time has elapsed, you'll find complete shifting of two uh, cycle positions. And this cycle span, okay, in the space we call wavelength. So it is shifting by one wavelength in one period. That's how it moves. So as one cycle in time completes, okay, the wave also advances by one cycle in space by lambda or wavelength. If that is the case, then we can establish a relationship for the velocity. Velocity means how much something moves in 1 second, right? Now we know that the wave completes if times if cycles in 1 second. Okay, in the time domain, I mean, you have cycles completed one whole t, but in 1 second, this happens if number of times. And when you complete every time one whole period t, the wave advances by lambda. So in 1 second, it advances f times lambda. And that's what is meant by Vp. So the velocity is frequency multiplied by the wavelength. Okay. So now you have, well, by the way, you can hear me, right? The sound is okay?
Yes, sir.
Yes, sir.
Okay.
Yes.
So we have got two different relationships for Vp. Earlier we had omega by k, of course for plane wave. And now we have Vp equals to f lambda. So we can equate. Omega we are showing as 2 pi f. So we can cancel out f. So now we have an expression for k, 2 pi lambda. Okay, so if you know lambda, then you can calculate k. Okay. Now I say that in the problems in the exam, if not, I mean, other is not mentioned, then you need to assume it is a plane wave, the velocity is the velocity of light, c. Okay. So actually you have here c equals to f lambda. Now if the frequency is mentioned in the problem, then you actually know lambda because you know c equals to f lambda. So whenever you find frequency available in the problem, then you know lambda. Then you can also calculate k from here. Okay. So the medium information is not required from frequency, you can calculate K. Uh, Small problems can be there in the exam using this sort of formula. I mean, we are not showing too much formula. I mean, most of the presentations avoid any formula. In this presentation, we have a few, but not too many. Now, the frequency, we can see that, I mean, it affects in different ways, like K depends on frequency, uh, the different phenomena, like we'll discuss penetration, uh, scattering. Okay, all these things are also dependent on frequency. So the wave propagation is largely affected by its own frequency. Okay, and this frequency range is split into different parts. So I'm talking about the radio frequency. Radio frequency goes up to 300 gigahertz. So now you see that ITU, International Telecommunication Union, uh, the major authority for all telecommunication standards, splits the whole range this way in a very organized way. Okay. Now, I don't think that you need to memorize this whole table. Okay. But at least you should skim through it. Okay. Get an idea. But here VHF and UHF, these terms are more commonly used because, I mean, wireless propagation. Okay, I mean, most of the deployments occur in this region, VHF and UHF, like say TV, okay, and many terrestrial links, say mobile communication also in this area. Uh, so these two terms, VHF for VHF and UHF, I think you should memorize, okay, the ranges for very high frequencies and ultra high frequency. Okay. I forgot, but I wanted to also add the frequency range for microwave. Okay, microwave frequencies. So I'm telling you now, later I add a slide. It is called microwave when the wavelength is in the order of centimeter. Okay. And if you relate with C equals to F lambda, you'll find that it is like 300 megahertz. It starts from this frequency. So there's the I mean theoretical range for microwave 300 megahertz through 300 gigahertz. Okay, so the last three parts in this table. However, now practically it is considered to start from frequencies around 1 gigahertz. Okay, so micro frequencies are actually in the gigahertz order. Uh, the term spatial term microwave is used because things start to work differently in the circuit when you have micro frequencies. Okay, I mean antenna-like actions can occur from ordinary circuits. Okay, I mean because since the wavelength becomes very small, special things start to occur. I mean there can be radiation from your own circuit. So you need to use different spatial methods when you have frequency in the microwave range. Okay, so that's why the spatial term microwave occurs, and there's also uh, so the practical range is from 1 gigahertz to 300, but you know that mostly we use frequency up to 100 gigahertz. Okay, so mostly it is 1 through 100 gigahertz. Okay, now there is also a term which came into prominence in recent years. It's called millimeter wave. So the wavelength is then in the order of millimeter. So now you know that it starts from Uh, well, let's see, 3 gigahertz, I think. Oh, okay, okay. So, but I mean, millimeter waves are considered from 330 gigahertz. Okay. So here the last part, the last part. Okay. Well, I'd say here actually, I mean, microwave. I mean, the centimeter, in terms of centimeter, you get actually from 3 gigahertz. Okay, but it is still the centimeter. I mean, it's an little uh, higher. But anyway, for micro frequencies, the theoretical range is starts from 300 megahertz. Okay, but for millimeter wave, it is the theoretical range starts from 30 gigahertz. But here the practical range starts from 10 gigahertz. Okay, so 1 gigahertz, the practical start frequency for micro frequency, roughly, it's not very strict limit. 1 gigahertz is the starting frequency for microwave, and 10 gigahertz is roughly the start frequency from frequency of practical millimeter wave. Okay, but ideally it is 30 gigahertz. This table I'm just showing. I mean, it's not our concern for wireless propagation. I mean, for wireless communication. Well, IR is used, infrared light, that is used for some wireless communication, like say your remote control that uses infrared light, IR. Although we are not covering this part in this course, but it could be. Okay, maybe I can add a small discussion of communication that uses IR.
Sir, could you kindly repeat the range for millimeter wave again?
For millimeter wave, the theoretical range is 30 gigahertz through 300 gigahertz, which is
Okay.
EHF.
Yes.
EHF. Okay.
Okay. Okay.
So you see the limit in wavelength. The lower limit is 1 millimeter then.
Yes, sir.
Okay. But practically, when you exceed 10 gigahertz, it is called
Yes.
millimeter wave. Okay. For microwave wave, you could say that, I mean, it is in the order of centimeter when they consider microwave. So you could say that it starts from 3 gigahertz. So SHF. But actually, it starts from 300 megahertz UHF theoretically.
Okay.
Okay, for micro it starts from 300 megahertz
It goes up to sir
up to
300
300.
gigahertz.
Yeah, they all go up to 300 gigahertz, which is the final limit for radio frequencies. However, for microwave, the practical limit is 1 gigahertz. Now, above IR, we have the visible light, and then ultraviolet. Okay, thereafter X-rays, all these in terahertz order. Okay, and actually this is above terahertz. Okay, gamma rays and cosmic rays. Okay. Oh, I thought I had shown this classification before.
No, sir.
But okay, I spoke of it. When you launch the electromagnetic wave in a way that it can propagate free, okay? I mean, free propagation is possible for the wave. So that is what you do when you use an antenna. So it is then called free EM wave. But when you let consider the coaxial cable, the electromagnetic wave propagates through coaxial cable, and you can bend the cable. Accordingly, the wave will also bend or change its path. So throughout the circuit, there are many other types of uh, guide that you can use, okay, in the circuit, and the electromagnetic wave propagates through the guide. So it can follow the path that you have within for the guide in the circuit. Um, so coaxial cable waveguide, these are just two examples. But I already actually uh, mentioned few things related to these two different types. Now here, let me tell you that in the case of coaxial cable, the wave propagates in the form of a plane wave. Okay, you still have a plane wave in the coaxial cable, but in the waveguide, it is not. In the typical types of waveguides, the wave does not propagate as a plane wave. Okay. So in the case of coaxial cable, those wave equations use k, but in the case of waveguide, it uses beta in place of k. Okay, any questions? You can interrupt me anytime
No, sir.
whenever you have questions. Uh, Finally, the direction of E and EH, well, okay, we already defined plane wave, and E and I mean, basically it is plane wave when you have E and H normal to the direction of propagation. In other words, there is no EZ or HZ component. E and H are vectors in the space. You considered voltage currents as vectors or phasors previously, but those considered the time variation. You drew phasor diagram showing voltage current as vectors, but those vectors represent the time variation. But here in the space, you have real direction for electromagnetic fields. Okay, so these are vectors in the space. In the rectangular coordinate system, there will be Ex, Ey, Ez, Hx, Hy, Hz. Now, if the direction propagation is aligned with Z, then for plane wave, there is no Ez or Hz components. Ez and Hz are zero. Okay, so you can have Ex, Ey, Hx, Hy. So they are normal to the direction of propagation. That's the definition of plane wave. However, the way we find the plane wave uh, for our purposes has also E and H normal to each other. And that's what we have for almost the whole wireless link. It's simple. Its analysis is simple. And I mean, the term impedance you always used for to uh, indicate the relationship between voltage and current in circuits. Now we have energy in the form of electromagnetic wave where we can use electric and magnetic field terms. Of course, once they induce, okay, or I mean, induce any circuit, then voltage and currents are induced there, okay. I mean, they will be generated in the circuit. But until you induce a circuit, okay, you don't have the voltage and current signals. You have the whole energy in the form of the fields, electromagnetic fields. So if you consider the transmission path, the wireless path in the air, then we have to work with these fields. Well, there also you have a similar parameter to relate E and H, like you relate V and I. And that is called wave impedance. Now, you have some propagation path area where this field these two fields maintain their relationship, or I mean they don't change their ratio, okay, over a certain distance. And when you have the ratio constant over certain path, certain over certain distance or part of the system, then it is called characteristic impedance. Okay. Uh, so here we call characteristic wave impedance, but the term characteristic impedance, I'm not sure if it is if you found it in any previous course. If not yet, you will find it in some course, I believe, where you have the same over a particular part of the circuit. The voltage and uh, current maintains its ratio. Okay. The circuit is such that over a part of it, you have the same ratio between voltage and current. If that is the case, then the ratio is called characteristic impedance. Instead of the term impedance, the term characteristic impedance is used, which means that this part have these characteristics, that its impedance is like this. So it is the characteristics of that part of the circuit. Um, so similarly, the term characteristic is used for the ratio of E and H, characteristic wave impedance. Um, now,
Sir,
yeah, yeah,
E and H are both field strengths, right?
right. E and H, yeah. E indicates electric field, H indicates magnetic field.
Sir,
Yeah,
is the characteristics wave impedance of plane wave? This is the last one, sir. But sir, when
yeah,
we are saying
right, right.
characteristics impedance and characteristic wave impedance, also there is a wave impedance in the second point, sir. So what is the difference, sir?
Yeah, I mean the
Yes.
first one here we have here three terms: characteristic wave impedance.
Yes.
So that is something that you use in the circuit. Okay, in the
Okay.
circuit you have voltage and current. In the ER you don't have. In the circuit you have voltage and current until your electromagnetic your fields are induced in a circuit. You don't get the energy in the form of voltage and current. Okay,
Okay, sir.
but in the circuit you have the energy in the in the circuit you have both voltage and current and the fields. You have both of them. Okay, and
Okay,
let me
sir.
tell you that for the circuit analysis also you could use E and H. That is possible. Like you did all the analysis, all the calculations using voltage and current. Okay,
Yes.
but it's possible that the voltage difference is always associated with some electric. There is an associated electric field. For current, there's an associated magnetic field,
Yes.
and there's definite relationship between current and the magnetic field, or
Yes.
the voltage and electric field.
Yes.
Okay, so the whole calculation could also be done using the fields, but that would be more complicated. The calculation would be unnecessarily more difficult or complex. Okay. So people avoid that, but it is possible.
Okay.
Okay,
So,
now,
sir, just one
mhm,
question, sir. Sir,
sure. Sure.
the wave impedance ZW,
Mhm.
whenever we are considering this thing for a plane wave, it turns into the intrinsic impedance of the medium.
Right. I mean, it is,
Okay.
yeah. So now, if it is a plane wave, then the wave impedance, okay,
Yes.
takes on a value that is independent of other things. Okay, it is completely dependent on the medium properties, and actually, it is the intrinsic impedance of the medium. I'm going to give you the expression for intrinsic impedance, but probably you already know it.
Okay.
So it becomes equal, and that is true for all types. Whether it is a free wave or guided wave. That means that in the coaxial cable, as I say, that you have a guided wave, but it is a plane wave. So in the coaxial cable, the ratio between E and H inside the coexistable is equal to the intrinsic impedance of what you have inside.
Okay,
I mean, between the two conductors, you have an outer conductor and an inner conductor. So
okay,
between
sir.
the two, whatever material you have, you can find out the intrinsic impedance, and that will be the ratio.
So the
Yeah.
second point is more of a general point, and
More.
the
Yeah.
third one is like a specific to
Or,
the plane waves.
yeah. Yeah. Right.
Okay, sir. Thank you, sir.
Now for plane wave, the intrinsic impedance uh, comes into role, and there, I mean, it has the intrinsic impedance is defined this way, completely material property. It's a ratio between mu and epsilon. Okay. Now, if you have air, okay, or if it was a free space, then you know mu naught and epsilon naught would have this value, and that gives you 377, almost roughly 377. So your if you have air or free space as the medium, then your intrinsic impedance is roughly 377 ohms or 125. Now in the problems, I say that the medium, if nothing else is specified, then you consider the medium to be air or free space, meaning that you all also assume that your intrinsic impedance is 120 pi. And to solve the problem, you may require this value. And I won't mention it in the problem because you should understand that it is known. Okay. So the assumptions that you will use in this course, okay, also include uh, is eta value or characteristic wave impedance, okay, or a ratio of E and H to be 125. That's the ratio of E and H. You may have to find out H, okay, and this ratio can help you do that. Now about power flow. You have a course, fields and waves, probably in this semester or in the next semester, that will show a relationship to calculate the power flow, amount of power that is flowing when uh, you are carrying energy using electromagnetic wave. Okay. So that's very important because I mean, in the case of say, circuit analysis, a lot of times you have to calculate how much power you are transferring from. I mean, you calculated voltage and current, but eventually you might have calculated how much power you're delivering to the load, because ultimately the energy that you can take to the load matters, okay, whether the purpose is fulfilled or not. That depends on how much energy the receiving side can can find finds they are available, and that depends on how much really power flowing or the electromagnetic wave is carrying. The calculation is very simple. You do a cross vector operation, okay, cross multiplication of E and H. So E and H, you need to take them with proper direction in the space. Okay. And the unit of P is watts per unit area. Okay, so how much power is flowing through per unit area, because the whole electromagnetic wave is propagating through some space and carrying power. Since we will have plane wave, usually we can actually use 90-degree uh, di difference between the position in any space between E and, as I said, that the E and H are in the, the typical plane wave that we find for wireless communication has These two fields also in normal to each other, so 90 degree. And then you see that the power value becomes E square by eta. Okay. Now note that we're not using RMS in the upper part. Well, for high frequencies, let me tell you, people usually don't use RMS. They use the peak values, the amplitude. Okay. So for high frequency courses, this one or microwave or any high frequency courses, uh, please don't use RMS in your calculation. RMS is used for low frequencies. So it is E square by eta. But if you used RMS, then you know that you would have, I mean, when you write down E, okay, in RMS value, okay, that is actually the amplitude divided by root over 2. Okay, so if you are using RMS values, then you get P like this. I mean, the expression for P will take on this form. Okay.
So, sir, for the
Yeah.
same formula, we'll have two values.
Yeah, I mean here E is in RMS.
Oh, okay, all right, okay. So overall, the value will become same.
Yeah.
Okay.
Oh, sorry. Give me a second. Give me a second. Did you do any mistake? If it is, then we should have 2 in the nominator, right? Okay, let me check. I think I was mistaken. We should have 2 in the nominator, not in the denominator. When you show RMS E, right? Taken. Okay. Okay, I'll correct it.
Okay.
Well, the final this part of our discussion on EMOF show this is the different polarizations that you have for the wave propagation, and there's an animation which clearly distinguishes these polarizations. But I already uploaded this video. You don't have to go to this link. It's available already in the Google Drive. I'll play it, but let me tell you the types. You have linear polarization, circular polarization, or elliptical polarization. And the top one is mostly used, linear polarization. The second one, circular polarization, also has these days a lot of use, but elliptical polarization has very little use. Okay. Now what they are? The polarization shows or tells you how the electric and magnetic fields are oriented. Okay, I mean you may have plane wave, but the way they change their position during as the wave propagates. Okay. So in the case of linear position, they actually don't change their orientation, but in other cases they do. They maintain a particular direction. So let me play the video. Okay, the left one is linear, then circular, then elliptical polarization. So it is showing the direction of electric field. Of course, normal to that, you also have magnetic field. Now you see I mean, at a particular instant, if you look at the linear polarization, as it propagates, okay, towards z, the wave advances. The, I mean, electric field has a particular direction, which is along this axis, okay. It is like 45 degrees between x and y. Whatever the direction is, always it has the same direction, okay, in the space. Okay, I mean, previously we showed it vertical. Okay. So it may align x or y, whatever. So that that particular direction it will maintain throughout the propagation of the wave. But in the case of circular, it keeps on changing the direction, as the wave propagates. So let's play. See, in the case of circular, the amplitude doesn't change as it changes its own direction. Its amplitude level doesn't change. Here it is, the amplitude level is indicated. Okay. So, oh no, sorry, the magnitude is indicated. It's the magnitude. Okay, so the magnitude is changing. Say at this moment, you have the amplitude, then the magnitude is dropping. Okay. But in fact, the amplitude does not change. Okay. If you, we know that the magnitude changes within the cycle, but the amplitude level does not change as it changes its direction. However, in the case of elliptical, the amplitude changes as the wave propagates. Okay, and you have them. The amplitude changes in the form of ellipse, in the form of the change of ellipse. Okay. It may not be enough clear for elliptical case because in the time variation you see the magnitudes. Okay, but in reality the amplitude level is changing. So,
Sir,
yeah.
so there are infinite sets of waves, right? Magnetic electric fields and the magnetic fields.
I
Or
couldn't
else
quite get
polarization won't be possible.
I couldn't quite get the question.
You showed that the electromagnetic waves are sets of perpendicular electric field and magnetic field, right?
Right.
So there should be infinite number of waves for this circular polarization, like in the
Infinite number of what,
is there only one set, sir? It's not only one set, right?
I'm not. I probably am missing something here. You have, I mean, electromagnetic wave propagating, and we're showing the direction of electric
Sir,
field.
the electromagnetic wave does not contain only one set, right? One set of magnetic field and electric field oscillating. It should.
Well, the term set does not fit in well here. You have, say, if you have a magnet, you have field around itself, right? So the whole space around the magnet is filled in with field. We don't use the term set here, that we have one set of field. And there is no actually distinct boundary where the field finishes, like light. Light is also electromagnetic wave. Okay. So if when you turn on a light, you don't have a, I mean, gradually the light dies out.
So I was actually talking the infinite planes, sir. Sorry.
Okay.
It's not actually the infinite sets.
Uh,
So the
Sir, if it is infinite plane, sir, it can be any amplitude, sir. So there is no bound, sir. I think he meant that.
no, sir. Like
Okay.
the fields like should exist in infinite planes, right? So it's difficult to
Yeah, that I mean, the visualization is not easy. Okay, we are showing the magnitude level here. So, okay, the electric field has some strength. So the electric field intensity is shown here. Right? The electric field, its unit is volts per centimeter. So that strength is shown here. You have the maximum value here. The value is dropping. Okay, I mean, you have the field in this direction. Okay. Uh, okay. Maybe I will. Uh, I mean, we can come back to this part again with more questions. Okay. Okay. That was.
Sir, one more question, sir. When we are saying this, sir, in our normal plane wave case, sir, there is the magnetic field, and perpendicular to that there is the electric field, sir.
Right.
So in that visual representation, sir, we saw that the কি বলে, there is like one line for the magnetic field that keeps on going, and perpendicular to that there is the one line for the electric field that keeps on going, right, sir? So in that diagram, sir, there is like only two lines that are continuing up to infinity, right, sir? So, sir, my question is, mane, are there other pair of planes with that? It's like only are these two the ones that are existing, or there are other electric and magnetic field present at the same time that are perpendicular to each other?
Got you.
Yes, I was actually asking.
Got you. Actually, yeah. Now I realized that he also asked the same.
Yes, sir. I just
Yeah.
explained what he
Right,
said, sir. Now,
right.
now I got it as well.
Yeah. Okay. Very good question. Great question. Actually, I mean, to answer it's a clear question. It is one set. It's one set. So, I mean, it is a control from your antenna, and the antenna's design radiates with one set. I mean, according to your set definition, okay, according to the way you use the term set. So, like the first one was linear polarization. So there, when I say that it is mostly used, then I mean that most of the antennas launch the signal in a way that you have the signal propagates with linear polarization. So that is what you do using your transmitting antenna. It launches the signal that way. So it's the job of the antenna designer to make sure that, I mean, it fulfills whatever polarization he wants to use. Then the electric field will maintain some direction. And here you see that there are two classes, horizontal polarization, vertical polarization. So that tells you the direction of your electric field. If your electric field is vertical to the ground, then it is called vertical polarization, meaning that after you launch, the signal is propagating far, but the electric field will always maintain its vertical direction. And when it is vertical, the magnetic field will be horizontal. So that is how it propagates. It keeps propagating. Okay. So now probably you understand that is actually it is one set.
That set will be determined by the antenna, sir.
By the antenna, yeah.
So without any polarization, sir?
Mm-hmm.
Without any polarization?
Without any polarization, no. This it uses some polarization purposely because from the receiving antenna, you have to the whole purpose of the communication engineers is to make sure that you have very good signal quality at the receiving end. Okay, so you can.
But so I was asking, like, without any polarization, if we don't add in, like, the waves we get from the sun, so do they have many sets, right?
No, there can be a combination of different polarizations, definitely. Okay, you can combine multiple polarization. It is possible, but wireless communication uses just one particular polarization. Let me tell you why. From the receiving end, so when you are using vertical polarization, uh, at the receiving end, you also need to set up your antenna at the in the same way for vertical polarization.
Yes, sir.
Then the reception will be the maximum. Okay. Now you must have seen wire-like antennas, just a stick. Okay, just a stick put somewhere vertically. Then the wave you have actually has vertical polarization. Okay, so in that case, you also need to put another antenna in the same way. That will also be, that has to be put that way, vertical. If you rotate the receiving antenna, the energy the reception will degrade. So meaning that the antenna orientation should match between the two sides. It's because of all polarization. Okay. You launch the signal with particular direction of your fields. When you catch, the antenna should also be oriented that way. So that direction of fields it needs to catch. And our next discussion is an antenna, but let me tell you now that the same antenna can be used for transmission and reception purpose. Okay, so if you use the same type of antenna, you need to orient actually the same way at the two sides. Okay, because it is launching with some particular polarization, the wave is propagating with that polarization, you need to catch it at the other end. So if you start using horizontal polarization, you just change the orientation of a transmitting antenna. At the receiving end, you must also change the orientation. Okay.
Sir, if
Yeah.
the receiving end orientation is not the same as the transmission one, sir,
Yeah.
will the
What will
signal
happen?
still be received or will it be
Yeah.
inefficient?
Yeah. That is what I was coming on to.
Yes.
What happens then? The energy reception will degrade as you keep changing your rotation. We actually had an experiment at our lab. We learned, first we use perfect matching, okay? The same way we orient the two antennas. And then gradually we rotate the receiving antenna. And then we can see that the power reception is lowering. Okay, so as we keep rotating from the other end, you have a certain drop of power. The further we rotate, the lower is the power. But when there is complete mismatch, okay, which is an orthogonal position, there is still some power. There are some reasons, but ideally you should have no power. Okay, ideally there should be no power reception. But one of the reasons is that there are, some waves created from different phenomena in the environment with different polarizations. Okay, and um, I mean, though they can be received by the receiving antenna. So that's one explanation. Ideally, you shouldn't have any reception, but practically you can have even good level of reception. Okay, especially depending on the environment between transmitter and receiver. Now note that although we are saying that it is horizontal or vertical, uh, and previously these types are mostly used, but we have a discussion after mid-semester which discuss the practical positions for mobile antennas. Then you'll see the polarization that we have shown here in our video, that electric field was inclined. It was 45 degree between X and Y, between vertical and, I mean, just in the middle, 45 degree shifted between vertical and horizontal. So it is called then plus 45. Okay, I mean, there can be plus 45, minus 45. Anyway, so that is widespread use for applications like mobile users, because when you hold your mobile across your head, the typical position is 45 degree, isn't it? Don't you hold that way?
Yes, sir. Something of that
Yeah,
nature.
yeah. So that gives you, I mean, the best position. Of course, I mean, it will retrieve enough power, however you put it. But if you consider the most usual position, it is 45 degree between vertical and horizontal. So when the base station launches the signal, it also uses 45 degree polarization. Okay, it uses linear, typically it uses linear polarization, but 45 degree alignment. Okay. Circular polarization, elliptical polarization, they have also actually quite a bit of use, especially for LOS communication. For LOS communication, a lot of times people use circular polarization. Okay, but I have few other slides here explaining each of these things. E, linear mean E and H always maintain a particular direction as the wave propagates. Okay, and horizontal means E is the, in terms of electric field, this horizontal vertical terms are used. For circular polarization, the projection of the head of E field is perpendicular to the direction of propagation, but it keeps changing the direction, okay, in a circular way, but maintaining the same amplitude. Okay, and it can rotate in, I mean, clockwise or counterclockwise direction. So accordingly, you have two different types. Like you had linear vertical, horizontal vertical. Here also clockwise, anti-clockwise. So here E and H rotates, but the amplitude keeps varying following an elliptical path. Okay, questions?
No questions. So
Okay, then let me move to our next discussion. Well, but before we do that,
so
let us
attendance,
set
sir.
a date. Oh yeah,
Oh, attendance.
and attendance.
So you're going to take it through the Google Classroom, right, sir? The attendance.
Hmm?
Are you
Yeah,
going to take?
I was thinking about doing that.
Okay, sir.
So please, all of you go to Google Classroom. I'm gonna. Okay, please go to the Google Classroom and write down your ID. Now we need to set a date for our first class test. Yesterday I spoke with Inan and he suggested the next Monday, which is 24th of this month.
Yes, sir.
Sounds good, Inan?
Yes, sir. Yes, sir. 24th of
Okay.
this month.
24th. And is 2 o'clock fine? 2 p.m. on that day? Is this time good for you? Inan and others, is 2 o'clock fine?
Sir, I think whatever Inan says, sir, that is okay, sir. Yes.
Okay, okay, very good. Now the syllabus, well, Inan suggested that it should be the classes before Eid. Okay,
Yes.
so what, I mean, is well, you already say that whatever Inan says,
Because sir, he's the
is
CR, sir.
actually,
So yeah, sir,
yeah,
it's best if
yeah,
he decides.
we
Sir. Yes,
must
sir.
rely on.
Yes.
Okay, okay, then I must agree whatever Inan says. Okay, then, but please make sure that I mean, the things are complete there. Okay, I mean, we say we are discussing Shannon's capacity, but few things might not have been enough clear. So yesterday in the beginning, I mentioned that.
Yes, sir.
So, but please consider that we had complete discussion on sound capacity
Okay.
before it. Okay.
Yes.
So, a few things I might have mentioned also later, but let's consider them complete. Okay, then those lectures will be our syllabus. Everything before Eid vacation. The format will probably like, I mean, in the Google Classroom, questions will be available, and like you are all familiar how IT takes the exam. So you need to make sure that you can use video. You need to turn on your video. Okay, there'll be Zoom link, and please log in 5 minutes before 2 o'clock and turn on your video. Okay, but the exam will start from 2 o'clock. I mean, the question will be available at 2 o'clock, and I think you'll have to write down on paper, and then
So what will be the
after,
question format, sir? The question format.
well, I create the questions at the last minute. Okay.
Oh, okay, sir.
But I mean, it will be a short exam, so there can be short questions or small problems, something that you can solve quickly.
Okay, sir.
Okay.
So what will be the duration, sir? Like half an hour, 15 minutes, 20 minutes?
It will be less than half an hour.
Okay, sir. All right.
Okay.
Okay.
Okay, then let's move to our next discussion, and it's antenna. The purpose of our new discussion on antenna is not to become antenna experts. Rather, the wireless, our focus is the radio propagation for wireless communication.
Sir, can we start this one next class, sir? Like, this is a new topic, sir, and we only have like 8 minutes left, sir.
Oh, really?
Yes, yes, sir. That is right. So if we start it, so the flow will be disrupted a little.
Okay, then let me at least tell you.
Yes, sir. You give us
why,
summary, sir.
Yeah,
Yes, sir.
what this presentation will also be pretty short. I mean, I'll go through it quickly because the whole purpose here is to make you familiar with the antenna operation, but not to make you guys expert in antenna area. Antenna courses are offered in postgraduate level. The antenna design involves real complexity. You need to have voltage and currents generated there, or electric and magnetic fields around itself, so that you get some radiation out of itself the way you want. Now, we'll be familiar with different terms that tell you how a particular antenna is radiating. Because for your use in a wireless link, you will be using antennas at the both ends. And with the antennas, you need to guide. Uh, you want the antenna radiation to take certain certain uh, pattern in the space. Okay. So this is called radiation pattern. How the antenna is sending its signal in the air, is putting the signals onto the air, okay, so that it propagates in a particular way. So the antenna design can control what we are calling radiation pattern. The most important factor here is how narrow or wide the radiation pattern is. Okay. So our antenna discussions will actually get you familiar with this, with the different terms that we can use to quantify how narrow or wide the radiation pattern is. Okay. So accordingly, you can select a particular antenna, that you have these different antennas available, and this type of parameter values will be shown for each of them. So you can select the one that fulfills your purpose. Okay. Once you are familiar with these parameters, what they mean to indicate your radiation pattern. Okay. So basically that is the purpose, and also there are different types of antennas. So we'll mention these types. Okay. So this can help you selection of an antenna for your purpose, but not to design an antenna. Antenna design concepts of theories are very complex. Okay. Our discussion will merely help you as an engineer to select the right antenna for your purpose. Okay. Okay, now questions. You're almost we're close to the end. So before we wrap up,
No
questions.
questions. No questions. Today's class was very good.
Uh, well, but actually, I have been, I mean, sort of slow so far. Okay.
Okay, sir.
I could not cover as much I planned to. So from next week, I'll try to go a little faster.
Okay.
If you feel problem in understanding, right there, you please let me know. So I can adjust my speed, but I'll try to make myself a little faster, so I can cover the all the useful topics. Okay, that's it for today.
Yes, sir.
Jazakallah for your time.
Assalamu alaikum, sir.
Alaikum assalam.